So, we started on transistors and we saw the physics of it, how the charge carriers move across the junctions and all that. Today, we will be talking more on its applications. So, let us first do some recap of what we did in the last lecture. So, bipolar junction transistor, this is the name. It is junction transistor because you have two p-n junctions, and bipolar you have two of them, is made of back to back two p-n junctions grown on the same semiconductor base. So, you have a schematic drawing like this, you have a thin region in between and then these two junctions here, and on the two sides you have another type of doping. So, you can have this so called NPN or PNP transistors. Everything is doped on the same semiconductor wafer by proper alloying or proper diffusion of dopants and in right concentrations and all those things. So, this is the variety. The middle region is lightly doped, this is very important, and is very thin, this is also very important, and that is known as base. One side of that base is heavily doped, which we called emitter, and the other side is moderately doped, and that is called collector. So, this is base, this portion which is sandwiched between the two parts, this is collector and this is emitter. Geometrical dimensions also collector, it is slightly wider in general than emitter, but the basic distinguishing factor is the doping. The emitter is heavily doped as compared to collector, and base is of course very lightly doped. Now, this is the symbol, this is the symbol. You have 3 elements, 1, 2 and 3, they are put in a circle in general, and on one of these lines you have this arrow, and that arrow tells that this is the emitter. So, this is the emitter part and this is the collector part. You have metallic contacts, so that outside batteries, resistances, capacitors joined at base or collector or emitter. So, you have those junctions from where you can join your external circuit, and this arrow tells whether it is NPN or PNP. So, the arrow is put on the emitter from P to N directions, P to N directions. So, if it is NPN transistor, this is N and this is P, this is N. So, on the emitter the arrow is from P to N. Similarly, if it is PNP transistor, this is P, this is N and this is again P. So, the arrow is from P direction, P to N direction, and essentially it shows you the direction of the current when the junction is forward biased. Which junction? This emitter base junction. Okay. Then normally this emitter base junction is forward biased and the collector base junction is reversed bias in normal operations, many of the applications. Two batteries are used for biasing these two junctions. So, if you have two junctions, let us say you have this NPN. Most of the discussion that I had done is was with reference to NPN transistor. The entire physics is the same. One can talk in terms of PNP transistors, the roles of electrons and holes will be different, swapped. So, if you have this NPN transistor, this will be the arrow. Then in this emitter side, if I put this emitter base junction, this has to be biased, forward bias. So, if this is P, you have to put a positive battery here, some resistance of course, and it goes like this. So, this junction is forward bias. So, this is a battery used for forward biasing this one. Then the collector part is also to be biased, and now collector base is to be reverse biased, and therefore, this remember this is N here and this is P here, N here. So, again you put a positive battery here and so on, some resistance, and so this is 2 batteries are needed for biasing 2 circuits. If these 2 batteries have a common terminal and that is connected to the emitter, as I have done here, this is known as a common emitter mode. Similarly, you can have common base or common collector modes. Then this emitter side is the input side and the collector side is the output side. Now, the very important thing is how it works, working of the transistor, and for that you have to remember that emitter is heavily doped and that emitter base junction is forward biased. And so, in that normal operation range, it gives lot of if it is NPN transistors, the emitter will inject or emit lot of electrons into the base region. So, that is why the name emitter. So, this emitter emits large number of charge carriers in the base region, majority charge carriers from the emitter, and when they go into that base region, there it is minority charge carriers. And since the base region is very thin, most of these carriers they cross over and go into that collector. So, that is why the name collector, it collects those charge carriers which are injected by the emitter into the base, and most of them are collected there, and some of them of course, they go into the base circuit or they recombine with some hole and some new electron is at some other place, is bond is broken and that new electron goes into the base circuit. Essentially, that makes that base current. So, this is what we had done earlier. Now, I will just elaborate little bit on this and then we will talk about the characteristic curves. Okay, so, the circuit looks like you have this transistor symbol. I am drawing this common emitter configuration and NPN transistor. So, this is N, this is P. So, it goes from P to N, NPN transistor. Then you have this base coming out and then outside you connect the circuit. So, you have a resistance, you can call it RB because it is connected to the base. Then you have a battery and then it is connected here to the emitter. What we are drawing is a very simple circuit just to tell the principles. The actual circuit will have many other things. And from the collector side again you have some resistance which you called RL or RC, and then you have again battery and then this is this. Now, if I look for the characteristics, what are the parameters that I have? This is the voltage that I have applied, this is written as VBB, I told you earlier, because this battery is connected to the base here, and this battery, this voltage is known as VCC because this side is connected to the collector. And then we have currents. So, it is forward bias. So, the current will go this way, which we call base current IB, and then we have this emitter current coming like this. So, this is emitter current IE and the collector current IC. So, input side, look at the input side. On the input side, if I take this voltage between this point and this point, let us say these 2 points, which is same as voltage between the base and the emitter. So, this voltage we will write as VBE. This is voltage between the base and the emitter. And then I have this current. So, IB is the current. Both of these are on input side. This VBE is the voltage which exists between this base and this emitter, and then IB is the current which is going in this input side of the circuit, and if I draw a curve showing the variation of I B as a function of V B E, that is known as input characteristics. And in this I have to keep V C E constant. What is V C E? What is V C E? V C E is voltage between the collector and the emitter. This one, this is the collector here, this is the collector, this is the collector, and here is the emitter. So, voltage between these two means voltage between these 2 points here, this point. So, the voltage between this point and this point here, that is our V C E. Between this point and this point, this is our V C E. Okay. So, this figure we will need again and again, maybe I will draw it again, but let us look at this characteristic. If this base emitter voltage is very small, that means this base emitter junction is forward biased by a small voltage. Remember, this is PN junction, and therefore, you have some kind of a threshold voltage. Before that the current does not start. It is diffusion, but then diffusion is against that potential barrier. So, for small biasing, forward biasing voltage, that barrier is reduced by a small amount only, and that does not allow a significant current. And therefore, what you expect is that the curve should start at a very slow increase note, and then once that threshold voltage is achieved, then suddenly it increases, the normal PN junction thing. So, what is the difference between that normal PN junction characteristic and this characteristic? The difference is, in normal PN junction, you whatever is emitted, whatever is coming from one side is going to the other side. In this particular case, whatever is coming from emitter, that means the electrons. If the other junction were not there, then all these electrons should have gone into this input side, into this base circuit. But because of that presence of that collector, because of the thin geometry of this base region, most of them are going into the collector, only small amount is coming in IB. So, the shape remains the same, but the values, if you look at the values will be very different. If it would have been a single PN junction of the same material, say silicon, this could have been in some milliamperes, 5 milliamperes, 10 milliamperes, but now it can still be in microamperes. It can still be say 5 microampere and then 10 microampere and 15 microamperes and so on, and the voltages could be say 1 volt here, 2 volt here and so on. So, this is known as input characteristics, where you draw this IB, this base current, against this voltage that this junction receives, that the base and emitter junction receives, and keeping this VCE constant, remember, keeping this VCE constant. So, that is the kind of input characteristics. You change VCE, the shape will remain same, but it will shift. It will be something like this. If you change VCE, it could be like this and so on. Okay. The other important characteristic is output characteristics. Again drawing the circuit, the same circuit. Okay. So, this is now the output side, and in output side I have this VCE. So, if I take my points here, this is VCE. So, voltage is this VCE and the current is this IC. Why I am putting arrow towards left? Because this is NPN transistor. The electrons are being ejected or emitted by this emitter, and electrons are being collected. So, electrons are flowing from the collector to this outer circuit, and therefore, the current is in the opposite direction. So, the arrow of IC is like this. So, VCE and IC. So, if I plot this relation between these two, that will be called output characteristics. So, let me start with this is VCE on this side and IC on this side. So, let us suppose it is sufficiently reversed biased. The collector base junction is sufficiently reversed biased. So, that whatever is emitted by the emitter, most of it is taken by the collector, and therefore, there is some current. So, a typical value, let us say we have 5 volts of this VCE. Remember, VCE is not the biasing voltage between collector and base, it is the voltage between collector and emitter. So, VC is here, this is collector and this is emitter, right. The junction is here, this is our base, this is our base. All right. So, VCE is not the biasing thing. If you call this as 0 voltage and suppose this base is at some 0.7 volt or so. So, this point is 0.7, and if this point is VCE, what you have is VCB. This is the actual junction voltage. This will be your VCE and minus that 0.7 volt. Or you can write that as VCE minus that VBE, and VBE is decided by the input circuit. So, if you put this VCE at 5 volts and if this VBE is 0.7 volt, then the reverse biasing voltage will be only 4.3 volt, but sufficient. So, in that case the collector is drawing all these electrons with full efficiency, and you have some kind of current which can be maybe somewhere here, let us say some 2 milliamperes or so. What happens if I increase this VCE? If I increase that VCE from 5 volts to say 6 volts by changing that VCC battery voltage that I have applied, the reverse bias voltage will be increased. Will it draw more electrons? Not significantly, because remember this is going from P side to N side, this is NPN transistor. So, it is going from P side to N side. So, I am only talking of that junction which is reverse bias. So, this is at the positive potential and this is at negative potential, and this is giving you some kind of a potential curve as a function of x. If you have some potential, it is, let us say this. Now, if the electrons are here with energy which is this much, and the electric field will just help it, and the electrons are going like this. So, the current is not decided by how much is this depth here, how much is that reverse bias voltage there. The current is decided by how many electrons are here above this level. So, even if you increase this reverse bias voltage, the current will remain almost the same. So, the curve will go like that. And if you reduce that reverse biasing voltage, what will happen? Again the current will remain the same, but if you reduce that voltage too much, what will happen? Suppose I reduce it to 0, suppose I make this VCE 0, what happens? If VCE is 0, what happens? What will be this VCB? That will be minus 0.7 volts. So, this will become forward biased. by 0.7 volts. So, when it was reversed biased, it was helping all those electrons, and therefore, the electrons were going towards the collector. Now, it is forward biased, and therefore, it will oppose those electrons, and therefore, your collector current will be almost 0. It is not allowing, it is putting up a barrier, and therefore, the current has to go to 0. Same happens if it is not minus 0.7, but say minus 0.5, minus 0.3 or even 0. So, in this region this junction will not allow those charge carriers to cross, and the current will be very small. So, at some stage this has to decrease from here, and then it has to go to 0. So, it goes 0 something like this. This particular point where the collector is not able to efficiently draw these electrons, or if it is PNP transistors holes, is known as saturation. The efficiency is saturated, it is no more drawing it, the reverse bias is not sufficient to draw the same number of same fraction of these charge carriers it was designed for. So, that is known as saturation region. So, in this particular curve, this part will be called saturation region. What has saturated? The capability of the collector to draw those many, that fraction of these charge carriers, that had saturated, and so this is known as saturation region. Now, this is for a particular IB. When you draw these output characteristics, when you plot this current IC as a function of this voltage VCE here, this VCE here, you keep IB constant. So, all these things is for a constant IB. Base current should be constant. If you are doing this experiment and drawing this characteristics, to keep this IB constant, you may have to change this VBB here. So, this VBB you have to change, you have to adjust so that this IB remains constant if you are drawing this output characteristics. What if I increase this IB and then draw this characteristic curve again? Suppose this is for IB is equal to let us say this is for IB is equal to 10 microamperes. What if I increase IB to 20 microamperes, and let us start again with this 5 volt point. This VCE is 5 volts, IB has been increased, and how did I increase IB? By increasing this battery voltage VBB here. So, if you increase that, you increase this forward biasing here, and then the current exponentially grows. So, you can change. Physically, what has happened? Physically, you have increased that forward biasing voltage a little bit, and more electrons are being ejected, emitted, injected by this emitter into this region. But collector is ready at 5 volts or at sufficiently high reverse bias voltage, the collector is ready to receive all those electrons which are coming, new electrons which are coming with the same efficiency, and therefore, proportionately IC will also increase. If IB has doubled, then almost in the same proportion IC will also double, and then the remaining discussion remains the same. So, if this was 2 milliamperes, now you will have let us say 4 milliamperes, your curve will be like this. And again, once it comes to that region 0.6, 0.7 volt region for silicon, where the reverse biasing is either very small or it has gone to forward biasing zone, you will have saturation. The efficiency of drawing these charge carriers by the collector has gone down, and ultimately that current becomes 0. So, this curve will be again it will be joining this point here and will go like this. Similarly, you will have more characteristics you can draw for different values of IB. You can draw the things. This could be 20 microamperes, that could be well looks like more than 30, maybe 35 or 32 microamperes. Let me write something. So, like that. These kind of characteristics are known as output characteristics. And why they are drawn? Why do people draw these characteristics? This is because when the transistor is used in the circuit, and in that circuit all voltages and currents they change, we know that what kind of response this transistor is going to give. So, that is why these characteristics are drawn. You can draw another set of characteristics which are known as mutual characteristics or transfer characteristics, in which you take one parameter from the input side, another parameter from the output side. You can take VBE, that input side voltage between emitter and base, and ask what is the effect on IC collector current, or you can just take IC and IB and ask what is the relations. So, these kind of characteristics can also be drawn, and they are known as mutual or transfer characteristics. Okay, now let me go for the applications. So, the most widely used application, and transistor is primarily known for that, is amplifier, as an amplifier. So, transistor as an amplifier. What is amplifier? That everyone knows. What is amplifier? If I am giving this lecture, there is a microphone out here, and whatever pressure variation in air I am producing, that pressure variation is driving some kind of a diaphragm here, and that is converting that pressure variation into electrical voltage variations. So, that we called a signal is generated, a voltage signal is generated, but that voltage signal, the amplitude of that signal could be very small. At that other end, at the receiver's end, how you are listening to this lecture, this voltage signal is amplified by some amplifier. The variations in voltages as a function of time, as I am speaking, I am creating variation in pressure as a function of time, and the voltage signal will just have that same pattern, but now it will be change in voltage as a function of time, and that has to be amplified, and that amplified voltage signal, that will drive another diaphragm of the speaker, and from there that sound will reach to the listeners. So, that is the purpose of amplification. You have some kind of signal, a small signal, whatever, I will not be able to draw it to the scale. So, this is the time here, and then you have this voltage here, right. This is the signal voltage, and then what you want is to amplify. You want to keep the relative magnitudes same, but all this is to be stretched. If you are on some kind of software file, maybe you just stretch that vertically, and you get the same amplified signal. Okay. So, that same variation in time, but then the output should be of the same variety, but of course, this vertical scale should be very, very different. So, that is the kind of thing that we need for amplification. And how do we use transistors to do this amplification? Well, simple. The circuit is of course, I am again drawing a very schematic type of circuit. The actual circuits are very different, just to understand the principles. That signal which we want to be amplified, that is to be added on the input side. So, you have this resistance RB is there, and then you have that VBB. So, together with that VBB you have to add this signal. So, this is that signal, small voltage variations in millivolts, let us say. The bias volt VBB, which is here maybe in volts, 2 volts, 3 volts like that, but then the signal is very small as compared to that, and it is time dependent. So, now your voltage, input voltage is becoming time dependent, and it's riding on this this thing. So, here we put this signal. Then we have again I emphasize this is only a schematic drawing. And we take our output from here, this is RL. So, qualitatively let me again understand it using our output characteristics. So, let us draw two characteristics, one corresponding to some IB, this is our IC and this is our VCE. Okay. And suppose we are somewhere here, comfortably reversed biased, we are somewhere here, and let us say at some instant you have some value of this signal, and therefore, there is some value of this VEB, this voltage here, and correspondingly there is a current IB, and for that current, let us say this current is IB, maybe let us say 10 microampere here, like that. And as time passes, this because of this voltage signal which is time dependent, this VBE changes. Okay. At some instant it is VBE, and then at a later instant, at time t plus delta, this becomes VBE prime, because this signal voltage has changed, let us say it has increased. So, what will happen? If this biasing voltage has increased, you will have larger forward current, you have more injection of those charge carriers from emitter to base, but remember the collector is ready to receive them, it is very well reversed biased, and therefore, the collector current will increase, and the collector current will increase, and where will it go? Just using this output characteristics you can determine. If this goes from, let us say 10 microampere to 12 microampere, if the you are going from this characteristics on this characteristics, has VCE changed? Think carefully. Because of the signal, this biasing of emitter base junction, that has changed, VBE has changed. Okay. Because of this current IB has changed, it has gone from 10 microampere to 12 microampere. Is VCE also changed? Yes, it is changed, because IC has also changed, this current IC has also changed. Now, you have larger IC, because you have larger injection of charge carriers and larger collection by the collector, and therefore, this IC has also changed. And if IC has changed, then this VCE is also changed, because if you look at this circuit, this is VCC, this is the battery voltage that we are giving, and IC is going like this is IC, and therefore, VCE is equal to VCC and minus IC times RL. So, if IC has increased, VCE will decrease. So, one thing is, if I look at the output characteristics from IB equal to 10 microampere, I have gone to IB equal to 12 microampere. From this curve I have gone to this curve, but I have also changed this VCE little bit. But if you are within this zone, this is not close to saturation, then it does not matter, your current does not change significantly. If this current here is few milliamperes, let us say this is let us say 4 milliamperes, and then this is 5 milliamperes. So, it does not matter whether you are here or whether you are here or you are here or you are here, your VCE is changed, but does not matter, the current will remain the same. What will happen to the output voltage? The output voltage VO, the output voltage VO, this is the output voltage also, this VCE is the output voltage if I am taking voltage from here. So, this is VCC and minus ICRL, change, that change in output voltage will be minus delta IC times RL. Your this battery voltage is same. So, what we are looking for in this output? We are looking for that variation, there is some DC because of that VCC and all that, but we are looking at that time dependent part. So, that change delta VO is just this much, and you can see here delta IC is in milliamperes and RL could be in whatever kilo ohm or 100 few hundreds ohms and like that. So, a small change in this input side because of the signal is creating some change in IB, and then that is creating a much larger change in IC, and therefore, much larger change in the output voltage, which is now minus delta IC RL. The minus sign is there, that means the output of this is pi at pi phase difference with the input. If your input is like this, then the output will be enlarged, but it will be like this, enlarged and inverted because your current is going towards left in this. So, this is how the amplification essentially takes place. We can do some more analysis on this. You can look at that input side also, and on the input side if I say that this is my VI, let us say that this is my VI input voltage, let us say this is my input voltage. So, the change in input voltage is because of this signal. So, I can write this VBE, VBE is equal to, let us write VBE, VBE is equal to VBB and minus IBRB. Check in the circuit, what is VBE? VBE is this actual voltage on this base emitter junction. So, you have VBB means including the signal, this VBB is okay, let me write plus Vs, plus Vs. So, VBB plus Vs is the voltage here, and then IB is there, RB is there. So, there is a potential drop here, IB times RB. So, subtract that, that will become this VBE. Okay. And so, you can write that delta VBE is equal to minus delta IB times RB and whatever is change in this signal, okay, delta Vs, whatever is change in your signal in that time delta t. So, this is like that, and delta VBE, if you can neglect, if you neglect, what is the justification? That remember that input characteristics is like this, you cannot change your voltage too much here. This is your VBE and this is your IB. So, you cannot change this VBE too much. If you change it too much, the current will be very high and your transistor will be destroyed. So, this delta VBE could be very small, and if you neglect that, what happens? What you have is change in your signal is equal to delta IB times RB. Look at these two equations. What is that delta Vs? That is your signal, that is how the signal is changing. So, that is the change in the input voltage, your signal which is time dependent, and output is right here. So, let me write what is the voltage gain. Which is delta V naught divided by your delta Vs signal. Look at back, delta V naught is minus delta IC times RL. So, let me write that minus delta IC times RL, and delta Vs is here, this is delta IB times RB, this one delta IB times RB. So, it is delta IB times RB, and this is what we had defined as beta. This is what we had defined at beta. So, this is beta AC and times RL divided by RB. So, that is the voltage gain, and remember, for a transistor this beta DC and AC are similar. If you are in the comfortable reverse biased and forward biased zone, this could be 50, 100 like that, 50 to few hundreds and so on. So, you have a voltage gain here, that is how the amplification works. Okay. Now, let us go for the another application, which is known as switching application. Transistor can be used as a switch. So, let us see what it is. The same diagram, you have this transistor in common emitter mode. Why I am drawing so many lines here and only I am showing 3 cells here and only 1 cell here? Nothing great about the numbers 1 and 3, but I am showing more voltage on VCC part and less voltage on VBE part. That is because you have to reverse bias this junction, collector based junction with at a larger, much larger voltage, then you have to forward bias this emitter based junction. So, that is why just to remind that that is the case, I draw this kind of thing. Now, let us suppose I do change this, suppose I change this VBB, and let us say this is our input Vi, and of course, our output is the same Vo. Okay. Now, if I plot this Vo versus Vi, what happens? Start with Vi very small, 0, let us say 0. So, that means I am forward biasing this base emitter junction with almost 0 voltage. I am not biasing it at all, and therefore, nothing will start. If you do not forward bias this junction, emitter based junction, this emitter is not injecting charge carriers into the base region. This I diffusion is same as I drift, and all those things are very, very small. and therefore, IB is 0. So, IB is 0. So, if IB is 0, then correspondingly IC is also 0. Of course, it is reversed bias. So, some reverse bias current can still be there and so on, but it is very very small. So, this IC is also 0. That gives me IC is almost 0. And if IC is almost 0, V out, remember this was VCC minus and then IC times RL. You had this IC here and RL here. So, potential drop across this will be RL times IC and this is VCC here. So, this VO that I am talking of is this VCC and minus IC RL. So, that is this, and IC is almost 0, that means VO is VCC. Okay. Essentially, you do not have a current on this RL, you do not have a current on this RL, and therefore, whatever is voltage here is the same as the voltage here. So, this VO is same as VCC, that is the message. So, if I put it on this diagram, this will be somewhere here VCC, this point is VCC, this point is VCC. Then I slightly increase this VI. If I slightly increase this VI from 0, once again that threshold is not reached, forward biasing diffusion current starts significantly increasing only after that threshold. For silicon it is around 0.6, 0.7, for germanium little less. So, even if you increase this VI little bit, the transistor or that emitter based junction is not really working, it is not really giving you charge carriers, not a large amount of diffusion is taking place there, and therefore, the same story will remain, and hence this curve will go like that up to some point where this forward biasing of emitter based junction is now significant and it is giving you currents. And once that is there, once you have reached that point, what will happen? After that, if you increase this VI further, what will happen? Now, you have everything functions well and you have a current, collector current, and once you have collector current, then your VO will decrease. Once you have this IC, VO is VCC minus ICRL, and therefore, it will decrease. So, it will go like that. But as VO decreases, remember what is VO? VO is nothing but VCE. This VO is nothing but VCE, collector emitter voltage. This end of this VO is here, this end is here, this is the emitter one, and the other end of VO is here, that is the this collector. So, this VCE. So, if VO has decreased, VCE has decreased. So, that reverse biasing is going down. Previously, it was reversed bias by say 4 volts, now it is 3 volts, 2.5 volts, 2.1 volts and so on. As you increase this current IC, VO will keep on decreasing, that reverse biasing will become weaker and weaker, and at some stage they will become almost the same. The voltage of base and collector will again become the same, and even if you go further, you are in the saturation zone. It is not properly reversed bias, sufficiently reversed bias, it has gone into the saturation zone, it is no more drawing more currents. So, even if you are increasing this input voltage, the IC remains the same, and therefore, your curve will look like this. So, you can draw 3 regions, this region nothing is happening. So, this you can call cutoff region, and here this has reached that saturation, that efficiency has gone down, reverse biasing is very weak, or even it has become forward bias. So, this is that saturation zone, and this middle one is called the active zone. Even on output characteristics you can draw that. Even here this was the saturation zone, this was saturation zone, we talked about this. It is not sufficiently reversed bias to draw the electrons, and this is active zone. This is called active zone. These ones are called active zones. This part is called active zones because now it is sufficiently reverse bias and it is active. It is active to draw those electrons. Okay. So, in the cutoff zone, this VO is VCC. What happens in saturation zone? If Vi is very large, if Vi is quite large, what happens? You are in this saturation zone. Okay. If Vi is very large, you are in this zone, in this saturation zone. So, once you are in this zone, what happens? Your VO is very small. So, your VO is very small, is almost 0. So, look at these two, look at these two. By controlling this Vi, if I put my Vi here, Vi is very small, almost 0, and I have output as VCC, large output, large output. Whereas, if Vi is here, if I increase this Vi, then it has gone into saturation and VO is very small. So, I can change this output voltage from a high voltage to a low voltage whatever threshold I put, by just changing this Vi and using this whole circuit. So, in digital electronics you need points where you have to put that point as 0 or 1, that means the voltage should be a high voltage or a low voltage, and that switching from 1 to 0, 0 to 1, that switching, that can be done using this transistor, controlling this input voltage and changing this input voltage from the cutoff zone to the saturation zone, that means from very low to very high. Very low, very high means say 0 to 5 volts and so on. You can make that switching of that point from high voltage to low voltage, 0 to 1, 1 to 0. So, that is how it works as a switch.